Hi, good evening. My name is Amit. This is week 6 of the problem solving session for the course Basic Electronics offered by NPTEL. The course number being NOC 23E62, as you can see. As I told you, this is the sixth session that we are doing. My name is Amit. I am a PhD scholar at IISc Bangalore, and for the past 5 weeks, to the past 5 sessions, we have talked about quite a bit. So this is the summary for that. In session 1, we saw Thevenin Norton equivalence, and then followed by nodal analysis, superposition theorem, and the phasors. In session 2, we saw some transient of RC circuits and RL circuits, and then the impact of switching. Let's say you flip the switch from position A to position B, and how did the transients change? And the transients effectively change because the topology of the circuit has changed. In session 3, we saw some diode based circuits like peak detector, clamper, and so on. Finally, in session 4, we saw one more important application for diode, that is the half wave rectifier with a smoothing capacitor, and we saw the ripple voltage over there, and finally the biasing of the BJT circuits. By biasing here, I mean the DC point, that is what VCE you wanted to operate, and what will be the collector current IC. And we saw that there are different modes: active, saturation, and so on and so forth. And then the DC biasing we saw, and how the circuit can change from saturation to cutoff to active mode. In the last session, that session 5, we saw an important application of for circuits of BJT, that is the common emitter amplifier. And there we saw the two things. First, again we saw the DC biasing, that we want to bias in active region for it to work as an amplifier. So we chose the bias support accordingly. And then secondly, we saw the small signal model, or the AC model as is often referred as. And the two models that we saw are the hybrid pi model and the T model. They are called so because how the BJT equivalent, small signal equivalent looks. And then finally we saw one more application of circuits of BJT, that is the push pull amplifiers, in which we saw an NPN and BJT amplifier, where only one of them was on at any given point of time, that depended on the input voltage. Typical push pull amplifier counterpart you can also find in the MOSFETs, which is CMOS technology. There we use PMOS and NMOS. So the working principle is quite similar to what what you might also see in case of MOSFETs. So that's for the past 5 sessions. And so now we'll begin today's session. Let me see. Yeah, so we'll wait for a couple more minutes, and then we'll start our session. In the meantime, if you have doubts, you can ask. Some people may join a bit late. I'm audible, right?
Yes, sir.
And the slides are also visible?
Yes, sir.
Okay, good. Thank you for confirming that. All right, let's get started now. So problem 1 says, the first problem is, let A1 be a common emitter amplifier. So A1 is a common emitter amplifier with resistance Re completely bypassed. So there's a resistance which we saw in typically these circuits there's resistance attached to the emitter, and the other end of the resistor is the ground. It's a completely bypassed. We'll see what this term means, right? And A2 is another common emitter amplifier with Re equal to Re1 plus Re2, where only Re2 is bypassed. So effectively there are two resistors in which only one Re2 is bypassed. So the resistance Re of A1 is equal to Re1 plus Re2 in A2. When we'll draw the circuit diagram, then these things will become more clear. All the parameters are identical in A1 and 2. Which of the following statements is true? So there are two common emitter amplifiers that are given to us, that is A1 and A2, and everything is the same apart from the bypassing of emitter transistors. When we draw the topology, it will become more clear. And now the options are, there are 4 options, only one of them is correct. We are required to find that. So first option talks about distortion. We'll see what this term means. Second talks about the input resistance. Third one talks about the IC, the bias current. And fourth talks about the voltage gain. The mid-band voltage gain we can assume in this case. All right, so what we'll do is that first we'll draw the circuits, whatever these A1, the how did circuit diagram for A1 and A2 look like, and then accordingly we'll try to investigate, we'll try to find out which of these options is correct by going into every option, right? So let's get started. So in this case, but we want to essentially, because remember the problem talked about bypassing, right? So we'll see that what do we mean by this term bypass, right? So this is, and now for this we need to study the role of bypass capacitor in common emitter amplifier. So but you see that in the middle, right, in this portion, this is your typical common emitter amplifier, if you just saw, and this is also the AC counterpart over here. You can see the voltage is, this is the DC voltage, and so this is the complete circuit diagram that we see. The capacitance that you see here, CE, it's called the bypass capacitor. Why is this called bypass? We'll see in a minute. And but in this is the, and this is the, what I'm defining as the full bypass. Okay, pardon the spelling mistake. This should be a single S. The full bypass. Okay, so just a second. Okay, so yeah, so we are studying this. So this is what I call the full bypass. You see this resistor RE over here, this is completely this is the RE and RC are completely in parallel. Okay, and in this case what I define as the partial bypass, here only RE2 is bypassed, RE1 is not bypassed. So what do we exactly mean by bypass? So what we mean is that when we apply the AC signal, right? So first let's see, if we ignore the AC, how does the DC equivalent for this looks like. So R1 and R2 will be the same, will be copied as it is. RC will be copied as it is, and RE will be copied, because in DC this coupling capacitors they will be treated as the open circuit, right? Yeah, my screen is visible, right? Can someone confirm? 1 second, please.
Yes, sir.
Okay, so this is the DC equivalent circuit for the full bypass. We ignore all the capacitances, CC, CB, CE. So this is how the equivalent DC circuit looks like. And let's draw the DC equivalent circuit for this. Again, CE, CB, and CC, right? They will be open circuited, so they will go out of the picture, and R1, R2, RC, and only RE1 and RE2 remain. So you see here, let's say this is RE1, and there will be another one. This is RE2. So RE1 and RE2 are in series, just like this, and we know that in the problem it's given that RE is equal to RE1 plus RE2. Okay, so what effectively this means is that these two circuits are equivalent. You see, the only difference between these two circuits is that there are two resistors in parallel here and this combined RE here, but as far as DC is concerned, RE1 plus RE2 is equal to RE, so electrically they'll be exactly the same. There will be no difference at all. What this means is that the collector current IC and the VCE will be same for both the circuits. Whatever VCE1, let's say, and IC1 is flowing through this transistor, the same will flow. IC, the same current and same bias will be for this. So DC wise are at the same plane. They are equivalent. Now let's talk about how does AC look like. So when seeing AC, so when we apply an AC signal, CE, CC, and CB, all three capacitors will be treated as short. Okay, and we also deactivate all the independent voltage sources. This means this independent voltage source VCC will be grounded, and you must recall from the lecture slides, this is how the equivalent circuit diagram will look like. So your VS will remain as it is, CB has shorted, CB is gone, they'll be in R2, and R1 is also connected between base and ground node. Now this potential is grounded. Okay, this potential is grounded, so R2 and R1 are in parallel, and then we replace the BJT with its small signal equivalent, which looks something like this. And since CE is 0, note, since the RE is bypassed, so this will be a short, so effectively AC short. So this effectively, what this means, that this emitter E1 is sitting at ground, AC ground. Hence you see this emitter connected to ground, right? This is the ground, this is the reference plane that we have over here. This is the reference plane, so this is grounded, and then RC and everything else remains the same, and this is the load resistor you can put, right? Let's talk about this partial bypass, the amplifier A2. So as always, CE, CB, CC will be shorted, and so will CE. Now if CE is shorted, RE2 gets vanished, because now there is clearly a short, so this resistance will not play any role, but RE1 will remain as it is. Okay, so how will the circuit diagram look like? So R1 and R2 will remain the same. R pi, GMVB, RC and RL remain the same as before. However, now rather than emitter being directly connected to ground, note here emitter is directly connected to ground. In this case, in A2, for A2 amplifier, emitter will not be connected to ground. Emitter will be connected to ground through a resistor RE1, which you can see, and this again we can treat it as the ground or the AC ground, which you see. So this is a key difference. The DC circuits remain the same, while the AC circuits are not the same. They're different. There is a resistance RE1 that's coming between emitter and ground over here, while it's a short. Okay, so just now we'll just ignore, since DC we don't care about, they are the same. Now we'll only analyze the AC part. Okay, so in this case, first let's talk about gain. How does the gain of these two amplifiers differ, and does it differ? So we know the gain expression is minus GMVB RC parallel RL, right? And VBE, this is the voltage VBE across base and emitter. This is nothing but VS over here, right? So I can simply write it as minus GM VS RC parallel RL, and the open loop voltage gain can be which is given by V0 by Vs, is simply minus GM RC parallel RL. This is fairly well explained in the lecture slides. That's where I'm referring to, by the way, all of these statements and diagrams. Now let's talk about now this circuit. Okay, this was the AC equivalent circuit for the A2, which is the partial bypass. So let's see what happens to the gain here. So again I write the potential Vs. Now how do you write Vs? This is this node Vs, the potential of this node. This will be nothing but IB times R pi, the potential drop here, plus the potential drop here. The potential drop here will be beta plus 1 IB, which is the current flowing through the emitter, times RE1. Right, from this expression you can obtain the value of IB like this, and correspondingly now V0 will be nothing but equal to minus beta IB. The current is flowing, the current will be the IC, so IC times RC parallel RL. The negative sign comes because the direction is in this, the current direction is flowing like this. Okay, and from this again you calculate V0 over Vs, and you get this expression beta RC parallel RL R pi. And then what we have assumed, that if we assume R pi is very small as compared to RE1. Note R pi is usually if you saw in the last class, R pi is usually small, like a few K. If beta is 100 and RE1 is again a few kilo ohms, right? This quantity is usually very large. So if you drop R pi, what's going to happen? Now the result will come out to be RC parallel RL over RE1. Okay, so you can clearly see the gain is different, right? Here the gain is RC parallel RL times GM, and GM is nothing but your GM is nothing but your transconductance over here, right? So the gain is different. So our alternate way of seeing is that since your input resistance has increased, now beta by R pi is nothing but GM, right? Let me write this. So you can also see it as minus beta RC parallel RL by R pi. Now you can see that the numerator is the same for both of them. However, the denominator is much higher. It's R pi plus beta plus 1 RE1. So what you can say that voltage gain, I should just a second. So what I can say that gain 2 is less than gain 1. because this denominator is higher here. I'm just comparing the magnitudes, by the way, not uh, the signs. Signs just denote that it will be out of phase. Okay, so this is, so the gains are different. So here this will have substantially lower gain as compared to the full bypass. Now what we'll do, so we have talked about gain, now let's talk about the distortion. So this is the full bypass that we have over here, right? So let's see what's going to happen, and we know VB equal to VBS. Again, I told you this is nothing but VBE over here, plus minus VBE. So VB is equal to VS, and we know that for the distortion will not be there. What is the condition for distortion to be minimal? That is when VBE, which is varying with respect to time, because note that we are applying a sinusoidal signal, should be less than VT. VT is the what for room temperature, which we show is 26 millivolts, right? The KT is also known as. So from this we can see that VS should be less than VT. So this imposes a restriction on VS. To avoid distortion, your input signal, the magnitude of that should be much smaller than VT. So let's see if there are some restrictions being imposed in case of partial bypass or not. So again, what we obtain is that now you can see from previous slide, you know that Vs is related to Ib, right? From this, what you can do some algebra and find out VBE over Vs. So this is VBE. This is VBE. So VB is nothing but R pi into IB, and Vs is nothing but IB R pi over beta plus 1 IB times RE1. So all of these expressions, IB is there in the previous slide. When you do that, you can obtain this expression that VBE over Vs is this. And again, the small signal condition will remain the same, that VBE, the magnitude of VBE, which is varying with respect to time, should be much smaller than VT. Then only you can avoid distortion. So let's do that. So let's put that VBE. So let's put the expression for BV over here. If you do that, you will get mod Vs, that's R pi over R pi plus Re beta plus 1. This expression will remain the same, right? It's actually Re1. It's Re1. Same goes for last slide also. Yeah, there it's Re1 itself. Okay, so it will be Re1 less than Y pi, and then it will, and if you take all the terms to the right side except Vs, what you will get is Vs less than Vt, R pi plus Re1 beta plus 1 over R pi. Right now, again, as we saw that usually Re1 times beta plus 1, which is much larger than R pi, which will effectively mean that this quantity Bs, so this quantity on your right hand side, which will be much larger as compared to the first result that we obtained, right? So we see that higher tolerance for Vs for A2. This is the takeaway from this, which this means is that a circuit A2, the partial bypass common emitter amplifier, can withstand much higher distortions, right? Because there's this huge term that is being multiplied apart from 2Vt, right? So much higher tolerance for Vs in case of A2 amplifier, right? And finally, we talk about the last option, which talked about the input impedance. So if you recall the expression, the input impedance will simply be R1 parallel R2 parallel R pi. These three in parallel, you can clearly see this is the input impedance for this circuit. For the partial bypass circuit, how will it look like? Rn2, which we are defining as, it will be R1 parallel R2 parallel R pi plus beta plus 1 Re1. So again, if you do some Thevenin equivalence, this is very straightforward to find out. Essentially what I am seeing is that what is the voltage drop that you are seeing, or what is the current that's flowing through here, and from this you can find out this is the expression. Now again, recall that this quantity will be much higher, this second term will be much higher than this term. Okay, so I can write it as approximately R1 parallel R2 parallel beta plus 1 Re1. Okay, in this all the three quantities might be of the same order. So let's say if you recall some of the problems that we discussed in last class, so usually R pi is a few k, let's say 1k, and these are also in terms of kilo ohms only. So even let's say it's 10k and 10k. Okay, so this answer will approximately in some kilo ohms. Okay, few kilo ohms. This will be 5k parallel 1k. In this case, let's again same this, let's say it's 10k and 10k, right? And let's assume Re1 is also 10k. this will come out to be 1000k. Okay, because assuming beta equal to 100, this is just a hypothetical case. I'm just trying to tell you, emphasize that this is, since this is much higher, right, this will not play a role. So this Rn2 will approximately be equal to R1 parallel R2, right, which in this case it's 5k, right. Here if you solve it, this will be 5k parallel 1k, so this will turn out to be 5 by 6, this will 0.87k. Okay, so you can see that, just an example, that Rn2 will be higher, the input resistance that we see will be higher than Rn1, and this comes out due to the fact that that there is this extra term being added over here, and beta is large, and Re1 is usually of the same order as R1 and R2 typically. So what what this will result in, that this will, we'll see that Rn2 is greater than Rn1. This is what we will typically observe, right. So now we are equipped with all the values that we should have been discussed, that we wanted to discuss. So we saw that first of all it says that let's talk about the first of all option A1 allows a larger input voltage amplitude without causing distortion in output voltage. So we saw that's not the case. We saw that higher tolerance for Vs for A2. A1 does not allow higher input voltage amplitude, it's A2, so this option is incorrect. A2 has higher input resistance, so we saw that Re2 is greater than Re1, so this is correct. A2 has larger DC bias current, no, we saw that they are DC equivalent, right. We saw that for the DC circuit was exactly the same for us, and this happened due to this fact, due to this line, resistance of Re of A1 is equal to Re1 plus Re2 in A2, so this option is wrong. A1 has smaller voltage gain, so let's talk about the expression for voltage gain for a second. So this was, and we saw that gain 2 was less than gain 1. Okay, we saw gain 2 was less than gain 1. So A1 has smaller voltage gain, no, it's A2 has smaller gain, right. We saw gain 2 less than gain 1, right. So among all the 4 options, A, C and D are eliminated, and only B is correct. All right. What I'll do, I'll pause here for a minute. If you have any doubts, you can ask me. But even before that, let me just repeat it. Let me just go through the question one more time, so that for better clarity. So what we were given essentially was that we were given these two circuits. This is the full bypass, where you can see that the emitter resistance Re is in parallel with a bypass capacitor Ce, right. So what this will play in DC, this will not play any role. This will be open circuit. All the capacitor will be open circuited. So DC circuits will remain the same for both of them. That is happening because Re here is nothing but Re1 plus Re2. So effectively DC circuits are equivalent, but there's a difference in AC circuits. Why? Because in this for A1, Re will be in parallel with the short when an AC is applied. So you can see emitter, this is emitter here, is directly connected to ground, which is not the case here. Here emitter is connected to a resistor Re1, which is then connected to ground. So Ce will behave like a short. That's why you see emitter is connected to a resistor Re1, which going ahead is connected to ground. And these are the two different circuits that you obtain for full bypass and partial bypass. And then we compared their gains, and finally the distortion, which allows higher distortion, and eventually the input impedance. So we saw that and this is the summary that we had obtained. This is that DC equivalent IC and VC will be the same for both A1 and A2. The gain is higher for A1, but despite having smaller gain in partial bypass, we see it has a higher input resistance, and more importantly it has a much higher tolerance to the input signal that we can apply. So depending on the application, we use either partial bypass or full bypass. That is the complete summary for this problem. I'll pause a bit over here because with this our BJT problems is over. This is the only problem for BJT. From now we'll step into the world of operational amplifiers. But before going there, I'll like to take a pause, and if you have any questions you may ask, or doubts or comments, whatever you have. All right, so if things are good, let's jump ahead. So as I told you, now we'll focus on operational amplifier. So operational amplifier, it's made up of two words, sorry. The first being operational. Operational means some operations. Some of the very basic operations in algebra are comparison, integration, differentiation, sorry, addition, subtraction, and so on, right? Logarithmic. So these operations can be performed using an electronic device known as the operational amplifier. Why amplifier? Because this typically you provided some input voltage and that it amplifies it, like we saw in case of the BJT, right? That there's a beta IC over IB, right? And you pass it through a load, then you can get some amplified voltage. A similar principle of amplification is being employed here. Third key thing to note is that this is a subclass of differential amplifier. So although I recall that this has not been talked about in the class, but it's just to keep in mind that this completes the whole picture. So even if you don't understand too much about this, don't worry. In the next class or something, this will come up. Okay. So by the way, this is the circuit diagram for a differential amplifier. So you can see that it has two inputs, V in plus and V in minus. This is implemented using BJTs, and here you see two supplies, VCC and VEE. So VCC, let's say, is plus 15 volts, VEE is minus 15 volts, and I'm taking the output in this fashion. Okay, I'm taking the output between the IC2 minus IC1, and the expression for this comes out to be like this: V out equal to AD, V in plus minus V in minus plus AC, V in plus V in minus over 2. So essentially you are in the first term, in the first term over here, this is the difference of inputs. Here it's average of inputs. What is AD and AC? AD is called differential gain, and AC is called common mode gain. So these are few different terms, but I told you it's a subclass of differential amplifier. So what do we need to do to this differential amplifier to convert it to an operational amplifier, right? So what we need to do is simply design the circuit in such a manner that AD is much larger than AC, and it has a low output impedance and a high input impedance, and what you will get is known as an operational amplifier. And this is the symbol of an operational amplifier. So you see this V plus is here like this V minus is here like this, and this Vs plus you see is nothing but VCC, this Vs minus you see is nothing but VEE, and this is the output, V out, that you see over here. So these two are equivalent circuits. This circuit can be converted to an operational amplifier provided we do these things. So how do we do these things? We design the circuit in such a manner. You choose the resistances and the BJTs and biasing in such a manner that you arrive at this condition. How do we do that? It's not of relevance to us, but it's doable. But for the part of this course and this session, what we'll talk about is the ideal operational amplifier. So this is how inner equivalent diagram of it looks like, right? But we'll not. What we do is that we take some parameters and see what's the ideal and the real world value. So for instance, let's first talk about the input impedance. Input impedance ideally is infinite. You see this input impedance ideally is infinite, but in actual cases it's a few mega ohms. Similarly for output impedance, you see this R out is 0. Ideally is 0, but the real value is a few ohms, right? And there's something called slew rate, because when you're applying, let's say, an AC signal to input, right, the output will also be oscillating, but sometimes the output does not change as fast as input, so there is some delay. That delay is measured using something called the slew rate, which is given in the units of volts per microsecond. And this is important. Common mode rejection ratio, so CMRR is nothing but 20 log AD over AC. I told you AD should be much greater than AC, right? If let's say AD is 3 orders of magnitude higher, so 10 to the power 3 over 10, 20 log 10 to the power 3, it will be 20 times 3 log 10, that will be 60, right? So if AD is much higher than AC, that is being, how do we quantify that? We quantify with a parameter called CMRR, right? And similarly, this is important, this is the most important thing, the open loop gain, usually denoted by G or AL or AOL. Its ideally its value is infinite. A real case scenario is more like 10 to the power 5. All right. So this is, but just to reiterate, we will be only talking about ideal operational amplifiers unless the problem says otherwise. All right. So these are the values. The key parameters are Rn that you see here, are out. These are the two which will keep on invoking over and over again, right? And again, this is the same diagram that we had talked about, but note that this time I've dropped the current the common mode gain, and that is because I'm assuming that CMRR is very high. So what this effectively means is that I'm ignoring the common mode gain, and I'm only interested in differential gain, which is denoted by this, and this is nothing but plus VSAT and minus VSAT. Okay, rest of the diagram remains the same, and you see now this configuration, inverting and non-inverting input. But this we'll see that when we see the problems, we'll see why I'm naming them like this, right? And so this is a very, I told you, this it's used to an operation amplifier used to perform some operations, and when one of the very basic mathematical operations comparison, like if x is greater than y or not, how do you do that? So you do that using this circuit diagram. So you see this is some V reference to the negative terminal, we are providing some reference, right? And this is the input that I'm providing to the positive terminal, right? So if V in is greater than V reference, right, the output voltage is saturation, is plus VSAT. So you see this region, I'll use a pen, a different colored pen, just give me a moment. Yeah, you see this region in purple. So here V in is greater than V reference, right? If V, this means positive terminal is seeing higher voltage as compared to the negative terminal, and thus the output voltage would be plus VSAT, plus VCC, you see over here. If it's the inverse case, and where it's, if V in is less than VRAF, which is the case in the third quadrant that you see, I'll denote it using the light blue pen. You see in this case here, V in is less than VREF, right? So it will be minus VSAT. So these two regions are called saturation region, positive saturation or negative saturation. But but in order to operate, in order to get some gain, we typically operate in the linear region, which you see over here, right? This is where we operate. And how do we operate in this region? Usually we apply an input feedback, right? So how do we what do we mean by feedback? So if the output voltage is being connected to either of the two terminals, it's a feedback. In this case, it's negative feedback because output voltage is being fed to the negative terminal of the operational amplifier. Hence, this is called as negative feedback. Usually, this gives a stable output, and some of the common examples are integrator and differentiator. On the other hand, if the output is talking to the positive terminal, which you see over here, right, this is called a positive feedback. This circuit is usually unstable, right, because this will quickly go to either negative saturation, positive saturation, right? Hence it's unstable. But it's not like it's useless. There are some important applications like Schmitt trigger or oscillators, which we'll see maybe in the next session. All right, so this is the takeaway from the operational amplifiers. So right now we are finished with the theory. Now we'll start solving the problems, but before that I'll pause here for a bit. If you have any comments or doubts, feel free to ask, because now we'll be solving the problem based on the theoretical understanding of what an ideal operational amplifier looks like, how does it behave. Now electrically, what are the values that we obtain for current and voltage, now that we'll see, and how to solve the problems. But this is theoretical. I'm just set the, how should I say, I just set the stage so that we'll go ahead and try solving the problems. All right, if there are no doubts, let's quickly jump to this problem. Okay, so this says that in the circuit shown in the figure, the op-amp operates in open loop configuration. Now this is important word, open loop configuration. We'll see how to identify what is the duty cycle D. Now duty cycle D, you must be aware of that defined as fraction of time V0 is high. So let's say V0 is the output over here. So let's say V0 is behaving something like something like this. Okay, it's a periodic function, and let's say this time is t1 and this time is t2, and this is the period over. So duty cycle will be defined as on time divided by total time period. So that will be t1 over t1 plus t2. So this will be a number always less than 1, and if you can also express in in percentage. So d in percentage is nothing but t1 over t1 plus t2 times 100%. All right, so we need to find when it's high, v naught is high, right? So as I told you in the previous slide, v naught can only oscillate since this is open loop configuration. V naught can either be high or low. It cannot operate in linear region, right? Because you can say it that there's no feedback to stabilize it. You can express it in this manner. Okay, so now we'll go ahead, but before solving any problem related to op-amp, you must do these speed checks. I recommend you do the speed checks. So first is the ideality of op-amp. Ask whether the op-amp is ideal or not. This is important. Remember we talked about ideality, like R out is 0, R in is infinity, right? If R in is infinity, let's go back there. This is important. If R in is infinity and no current can flow here, right? I in, I'll write if Rn tends to infinity, I in is 0. There can be no current flowing into or out of from the input side, correct? This is important. That's why I talk about the ideal operational amplifier. So and this would mean that I in is equal to 0. There will be no current flowing into the operational amplifier. Second, what you check is nature of feedback. So what kind of feedback is there in the problem? How do you check that? You stand at the output and try to go to the input without going through the triangle to the operational amplifier. So how to get from V0 to either this terminal or this terminal? There's no direct way, right? There's no pathway around here. This means there's no feedback. So we'll see in this problem, no feedback, right? This third principle is usually called the virtual short, but this effectively means is that this non-inverting terminal and this negative, also known as the inverting terminal, it's as if they are connected, they are at the same potential. They're not exactly at the same potential, but their potential is more or less same. Why is that happening? This is again happening due to the fact that I in is 0. The I in is approximately equal to 0. So you see that if there is no current, that is, this is Rn, right? So and let's say this potential is V plus and this potential is V minus. So I'll write Ohm's law across Rn. So I'll say I in times Rn should be equal to V plus minus V minus, and in ideal operational amplifier we assume that no current is flowing, right? So what we'll see that V plus is approximately equal to V minus. This condition is known as virtual short, right? There will be some difference because that's why this approximate sign, but for the problems that we are going to encounter, we'll assume that it's a virtual short. Okay, again, this is a key thing. So these are the pre-checks or assumptions that we make, right? Now based on these assumptions, now let's go ahead and try to solve this problem. All right, so let's do that. So again, I'm assuming this to be okay, so let's just try to find out this potential V minus and V plus. Okay, now what we are required to find, we are required to find the duty cycle. Okay, so let's do that. Now to do that, first let's try to identify what's the potential of this node V minus. So how do we do it? We find V minus using, this is nothing but a potentiometer, right? Because using voltage divider, whatever you want to call it, sorry, not potentiometer, voltage divider. So I can simply write V minus is equal to R2 over R1 plus R2 times 3 volts. This will come out to be 2 over 2 plus 1, 2k over 2k plus 1, 3k. This will come out to be 2 volts. So V minus is fixed at 2 volts. Remember I talked about a Vref. This is the same thing. This is the reference. Now negative is fixed to some reference of 2 volts. Now what we'll do, now in the second part, since Vref, which in this case is V minus, is 2 volts, right? V out will be equal to plus V sat if V plus is greater than V minus, and minus V sat if V plus is less than V minus. This is nothing but the this is how a comparator will operate. So V naught output voltage will be plus V sat if V plus this voltage is greater than this voltage, right? So what this would mean is that, so what I can say is right, so let's let's just consider only only one time period, okay, because it's a periodic signal. So whatever happens in the first time period will eventually keep on happening. It'll keep on repeating till infinite time, right? So what I'll do is that, so we know this voltage, right? This is 2 volts, right? V minus is coming out to be 2 volts. So let's just see, let's just find out the time. So in the third step, we find time t equal to t naught when V plus is equal to V minus, because that is the point at which V naught will switch, okay? So how do we do that? We'll simply, for sine omega t naught minus 1, this should be equal to 2 volts. When V plus, this is the expression for V plus, this is the expression for V minus. So from this I'll get sine omega t naught, this will come out to be 3/4. Alright, sine omega t naught is 3/4. Now we are required to find the time period on which this is high, okay? So what I'll do is that I'll assume simply omega t naught equal to theta naught. Sine theta naught equal to 3/4. This is the time at which switching happens. So switching happens at theta naught. What do I mean by that? I mean this. So let's draw this signal first, okay? This is 4 sine omega t minus 1. So at t equal to 0, the value is minus 1, that is here. And then at some, when omega t naught reaches pi by 2, when omega t reaches pi by 2, this will be 4 minus 1. So this will be 3 volts, somewhere over here. 3 volts. And then it will go negative, and then it will be minus 4 volts. And as I told you, I'm only drawing the one cycle. This is V in, okay, and this is one complete cycle. So this is, this time will be t by 2, and this time will be t. T is the time period, all right. And this value is plus 3, this value is minus 4, and we know that V reference is I think plus 2. Yeah, so V reference is plus 2, that is somewhere over here. So this is your V reference, all right. So this is the V reference. Then what we need to find, we have just found out this time, right? We have just found out what is this time, and we came to know that the time period t naught corresponding to this, we find this is what we had assumed to be t naught, right? So now what I'll do is that, so we know, we just, so whatever, so since, now next thing, let me draw the output voltage also here. This is V out. So we know that when V in is less than V reference, so till this time the output will be minus V sat. The output will be somewhere here, and then after this becomes high, it will go high like this, and then again it will go low, and it will remain low for a long amount of time, and then it will go up again. So this is the second cycle that's starting, right? So this is what I talked about. So this is the on time that we are required to find, the duty cycle corresponding to the on time. Now so if we know this t naught, right, so we know that sine theta naught. So let's, so in the last slide we had obtained sine theta naught equal to 3/4, right? So now just try to evaluate what is the theta that's corresponding to this, okay? That's simple. That's sine inverse 0.75, sine inverse 0.75. Now that comes out to be around 48 degrees. All right, so this means if I express this in terms of, rather than time, if I express in terms of theta, so this from here to here is nothing. This is 0 degrees, this is 48 degrees. Okay, so now you can see, so this means that this time period, right, is again 42 degrees. So now what I'll write that theta on, right, till what time is it on? So it's on only during this amount of time, right? Only during this amount of time is the is output high, right? So if I put theta on, so this means it's on only for this much amount of time, right? This time here. So that will come out to be 90 minus 48 degrees. That's in the first quadrant, right? And then same will be repeated for this half, that's why into 2 over 360 degrees, because 360 degrees is the total time that it takes. Okay, so if we solve it, so 90 minus 40 is 42, yeah, 42 times 2 over 360 degrees. So that will come out to be 84 over 360, comes out to be 0.23, right? So actually I should say it like this, that just give me a moment. Yeah, so this is theta on. This means the duration in which it is on. So this is 42 times 2, which is 84 degrees. D will be theta on over theta total. Theta on is 84 degrees and theta total is 360 degrees, which comes out to be 0.23. Rather than solving it at time, I'm just solving it in theta, because omega t naught, remember, we have assumed to be theta naught. Since we don't know omega, it's better to do it in theta, and then that's how we did it. So the key thing here was that to identify the reference voltage, which we got using this voltage divider, and then we just obtain the time at which V plus switches. So just when V in crosses this point, right, it will go high, and then again when it crosses this point, it will go low. So it's on during this point of time, which I obtained. I calculated this T naught or theta naught, comes out to be 48 degrees. So it's on only in the when it's going up, it's only on this point is 90 degrees, by the way. This point here is 90 degrees. So 90 minus 48 is the time in which it is high in the rising cycle, in this first cycle, rather than rising cycle. So 90 minus 48 plus, it will be same on during this period. So 90 minus 48 into 2, and it's off from here till the next cycle comes. So that's why 90 minus 48 into 2 is 84. The theta total is 360 degrees, and hence the answer comes out to be 0.23 or 23%, however you want to express it. All right, so let's pause a bit. If there are any comments or questions, please go ahead. All right, now let's go ahead for the next problem, which is over here. So in the op-amp circuit shown in the figure, what is V0? Very straightforward question. We need to find the output voltage for this given circuit. Okay, as always, we'll do some pre-checks. So what is the ideality of op-amp circuit? If the question says nothing, assume ideal. I again reiterate why we are assuming ideal. This means R on is 0, R in is infinity, and this effectively would mean that I in is 0. There's no current flowing into the op-amp. And what is the nature of the feedback? You take the output and you try to go to any of the inputs. Now you can clearly see this output here, it's connected to this negative terminal. This means it's a negative feedback. Negative feedback. And we saw that negative feedback circuits are usually stable. And the third thing which we see is the virtual short. So what do we mean by virtual short? We saw that this negative terminal, positive terminal are almost equipotential. Why is that happening? We again saw that when operating in the linear region, right? So this is also true when there is negative feedback. Plus linear operation. We saw two regimes, right? There was one linear regime for an operational amplifier. We saw this kind of behavior, right? So this is sorry, my bad, just a second. So this is V out, this is V in. We saw a behavior something like this. So this is the linear region that I'm talking about. So when you are in here, if you go to the, if you refer to the lecture slides, there Professor Patil talks about then give some negative feedback and linear operation. But since V in is so small, right? So V, if you recall, AV is nothing but V out over V in, right? So V in is nothing but V out over AV, and AV is usually very large, right? So that's how we obtain, that's how we come to the conclusion that these two terminals are almost at the same potential. Okay, let's go to the lecture slides for more clarity. I'm not going to repeat it here, but we'll utilize this information to solve the problems. Okay, so remember that this is the virtual short, right? So we are required simply to find what is V naught. Let's quickly now label the voltages. So let's call this voltage V, and sorry, V plus and V minus. So as always, find V plus using potential divider. So we do that, we find V plus will be nothing but equal to 0.6 times 1k over 1k plus 2k. This will come out to be 0.2 volts. This will be 1 by 3. So V plus is coming out to be 0.2 volts. Now what this would mean is that this would mean, since virtual short, V minus is also equal to 0.2 volts, right? Now as a step 3, what we'll do is we'll apply KCL at inverting terminal. What is the inverting terminal? This is the inverting terminal over here. Let's apply KCL over here. Okay, so let's draw some currents. Let's call this I1, let's call this I2, and let's call this I3. Remember, no current can flow inside this op-amp, so I'll simply write inflowing currents are I1 plus I2. This should be equal to, okay, sorry, I made a mistake. Let's apply the KCL. Let me, sorry about this. Let's apply KCL at this node. Let's call this node A. Okay, so KCL at node A. So if we do that, we'll find incoming current is I1, right? And now note that I2 is flowing here and no current can flow here. So I2 will also be coming like this, right? So I1, incoming flowing current at node A is I2. This should be equal to outgoing current, which is I3. So let's evaluate the expression for I1. I1 would be 0.2 minus 0.2. This node is also at V minus, which is 0.2, by 1k, plus the expression for V2 will come out to be minus 0.5 minus 0.2 divided by 2k. This will be equal to I3. I3 will be nothing but minus 0.2, the potential here, minus V naught over 2k, which is the resistance value that we see here. This term comes out to be 0. This comes out to be minus 0.7 over 2k. This comes out to be minus 0.2 minus V naught over 2k. 2k and 2k gets cancelled. What I get is V naught plus 0.2 equal to 0.7, which means V naught comes out to be 0.5 volts. So V naught for this problem is coming out to be, sorry, did I make a mistake? Just a second. Sorry, this is plus 0.2, not minus 0.2. This is plus 0.2. So it will be, let's do this again. So I'll write it on the next slide. So I am getting minus 0.7 equal to 0.2 minus V naught. This will give me V naught equal to 0.2 plus 0.7, which comes out to be 0.9 volts, which happens to be option A. Now just to quickly summarize, what we did was that Again we applied some, remember all this P check, this is important. I'll keep repeating them, right? So first we find out the potential, this V plus, which is simple, this is nothing but a potential divider. We obtain its 0.2 volts. Due to the virtual short condition, the voltage at this negative terminal will also be V minus, and the voltage at node A will also be V minus, which happens to be 0.2 volts. We simply apply KCL at node A, which is the incoming current I1 plus this current coming here. Now what is the current here? Since no current can flow here, so I should write this I is equal to 0. So all the I2 that's coming must flow over here, right? So second incoming current is I2, I1 plus I2 equal to, not minus I3, it's I3, that's from 4, yeah. So I1 plus I2 equal to I3. I put the current expressions for all these three, I1, I2 and I3, and we obtain the value of V0 to be 0.9 volts. So this is a fairly straightforward problem that we did. Now the key thing to notice is that, so you see that here we are providing inputs to both the terminals, right? V plus as well as V minus, but the output voltage is not saturating because we are operating in linear region, right? Because you are operating in linear region, and we see there is negative feedback. That's why I told you this is the assumption that we have, that it's a virtual short. So it's good to just revisit your assumptions that you have made after the problem is complete. So we do that. Any doubts, any comments till now? All right. So the thing about the problems for operational amplifier is just the first stage, where you have to identify the feedbacks or the pre-checks that we do, right? After that it's very simple, it's just KCL and KVL. There's no scope of getting it wrong once you identify the problem, and that is the critical part for this. All right, so in this problem we are required to find gain V0 over Vi. This is the output voltage V0, this is the input voltage Vi. We are required to find the gain, right? As always, the pre-check. So if nothing is given, ideality, we assume it to be ideal. Again, what do we mean is that R out is 0, R in is infinity, and I in is 0. This means no current is flowing over here. This I is 0, I is 0, also for this, no current flows here. All right. And the nature of feedback, so here there are two operational amplifiers, right? So let's check the nature of feedback for each of them. Let's talk about this first. So here it's the output here, and this output is connected to the negative terminal, so the nature of feedback is negative. Let's talk about the second op amp. This is the output and it's connected to the negative terminal, so it's again negative. And we saw the negative feedbacks are usually stable, and so let's see that what the current gain looks like. And again, the virtual short condition we saw in case of negative feedback and linear operation, assuming these things, we saw that we can assume the virtual short, but that means is that this potential is same as this potential, and again the same goes for this. The inverting and non-inverting terminal are sitting at the same potential. This is not a physical wire, again repeat, these are approximately similar, right? All right, so let's go ahead and do that now. Now what we need to do is that just let's assume the potential of this node to be V1. Okay, right, so let's assume this to be V1, and now what I'll do, due to the virtual short, now I know that this will also be Vi. Whatever the voltage that we're seeing here, no voltage can be dropped here because there is no current flowing. Remember, there's no input current to this, so this voltage will appear at V plus, the same voltage will appear over here, right? And also same voltage will now appear over here because this is nothing but a wire, correct? So now what I can do is now and again remember that no current can flow here because this will be flowing in or out of the op amp, which is not possible. So whatever current is flowing through here, right, let's assume this current is I1, and the same current will flow through here, right? I1 should be equal to I2. So as a first step we see, so we label the voltages for A1. Let's call this operational amplifier A1, this is A2, okay? And we see I1 equal to I2. So So when we see I1 equal to I2, so let's just let's just write the expression for I1. This will be V1 minus Vi over 10k. This is the current flowing. I2 will be nothing but Vi minus 0 over 2.7k. If you solve this, V1 will come out to be Vi 1 plus 10 over 2.7, right? So let me get my calculator and quickly evaluate what this turns out to be. This is 3.7. This comes out to be 4.7 times Vi. V1 is 4.7 times Vi. What this means is that the output, this voltage V1 is magnified by amplified by 4.7 times as compared to the input voltage, and in the same phase. Note, I told you we'll talk about inverting, non-inverting amplifier. This is known as the non-inverting terminal. Why? That is, if you apply input voltage to this, the output voltage will not be inverted, will be in the same phase as this. Okay, this is what we mean by that. All right, so this is the analysis for A1. Now let's do analysis for A2. All right, so again this is the virtual short. This is grounded because again no current can flow in, so whatever potential is here, this will be the same, and this will also be grounded. All right, so now what I'll assume that a current I3 is flowing like this, and again no current can flow into this operational amplifier, so I3 will again, let's assume it to be I4. Okay, so analysis for A2, we see that since In is 0, this implies I3 should be equal to I4. No current can flow here. So what is I3? I3 I can write as V1 minus, what is this potential? This potential is 0, right? This is grounded. V1 minus 0 over 1.2k. This will be equal to, this is 0, right? 0 minus V0 over 8.2k. This will give me V0 equal to minus 8.2 over 1.2 V1. Let's see what this comes out to be. 8.2 over 1.2 is coming out to be 6.83 minus 6.83 V1. This is V0. Again, the voltage here is amplified with respect to this voltage, which makes sense, by a factor of 6.83, but this is a negative sign. Why this negative sign? Because note that the input to this operation, input to A2 is coming on the inverting terminal. And why again this signifies the term why inverting terminal? Because the output voltage is out of phase by 180 degrees or inverted with respect to the input voltage. Hence this terminal is also known as the inverting terminal. Now we are required to find V0 over Vi, right? But we have found out V0 over V1, and we also know V1 over Vi. I'm just placing it like this. V0 over V1 we calculated was V0 over V1 was minus 6.83, and V1 over Vi, if you calculate, if you get it from this is 4.7. You multiply them, this comes out to be minus 32.12, which happens to be option B. Let me check. Yeah, option B is the correct one. So this is a good problem. So this was again a negative feedback, but this was a non-inverting amplifier because the input is being applied to the positive terminal. This was an inverting amplifier. And again you see one very powerful thing here. If there are multiple amplifiers cascaded, you can simply multiply their gains. This is the gain for the first amplifier, this is the gain for second amplifier. If there is a third amplifier, or usually called in third stage, the gains will simply get multiplied. And this magic is happening due to the fact that no input currents are there. It's an ideal situation, and that's why we are seeing this. All right, any comments, any questions? So this was a good problem actually, because usually this is cascaded, many different names. It's called the cascaded configuration or two-stage amplifier. So there are different names to this. And you see the negative sign again, that means is that V out and V in are out of phase, which makes sense because this does not invert the phase, but this inverts. So only 180 degree flip and hence the negative sign here. Right. Assuming the op amp is operating in the linear region, what is V naught? So this is the circuit diagram that is being given to us. Pre-checks the ideality of op amp. Again, we assume if nothing is given, we'll assume again why we essentially we are assuming R naught, R in is infinity, R naught is 0, and I in is 0. This means there's no input current. So this current is 0, and again this current is 0, right? Nature of feedback. How do we do that? You stand at the output voltage and try to go to the operational amplifier. So you can see that there's a negative feedback and there is a positive feedback. Negative and positive. Virtual short, will it be applicable? Yes. The problem itself says we are operating in linear region, and hence the virtual short. This means that these two terminals sitting at the same potential, we can directly apply that. Okay, let's do that now. So first we'll have to assume some potential. So since these are at the same potential, let's assume this potential to be V. Okay, so this is also V, this is also V. Now what we'll do is we'll first do KCL at inverting terminal. Inverting terminal means the negative terminal, this terminal. So let's do KCL here. So we'll assume that a current I1 is coming and a current I2 is going like this, and again there'll be zero current flowing here, right? 0. So I can say incoming current I1 equal to 0 plus I2. The value of I1 will be simply V1 minus VI minus V over R1. This will be equal to 0 plus I2 will be V minus, this is the potential V, minus V naught over R2. This is our first expression. Now we are required to find V naught. Okay, so let's just try to evaluate the value of V from here. Okay, now I'm putting the values. So 0.4 minus V over R1 is 4.7K. This is nothing but V minus V naught, we don't know. The value of R2 is 12K. So what will this give us? This will give us so if I cross multiply, so that will be V minus V naught equal to 12 over 4.7 is 2.55. so this is 2.55, 0.4 minus V. This will give me V equal to V minus V naught this will be 10.2 minus 2.55 V. This will give me 3.55 V minus V naught equal to 10.2. We have to find out V from somewhere. How do we do that? We simply apply KCL at non-inverting non-inverting terminal, which happens to be this terminal. So again, whatever the current is flowing through here, let's assume it to be I3. This current is I4. There can be no current flowing through here. So I'll simply write incoming current I3 equal to 0 plus I4. This will be 0 minus V. This potential is V over R3. This should be equal to the value of I4 will be nothing but V minus V naught over R4. So this will give us minus V over 8.2K equal to V minus V naught over 91K. Okay, so this will give me V minus V naught equal to 91 over 8.2 is 11.1 minus 11.1 V. So this will give me that just a second. Yeah, so V naught will become equal to 12.1 V. Okay, now let's put this value here. So this will come out to be 3.55 V minus 12.1 V equal to 10.2. This will give me V equal to 10.2 over, this will be negative sign, 12.1 minus 3.55. Let's see what comes out. But this comes out to be 12.1 minus 3.55 this will be divided by 10.2 divided by answer. This is coming out to be minus 1.2 volts. So expression, the value of V comes out to be minus 1.2 volts, and thus V naught, which is nothing but 12.1 just a second, yeah, 12.1 times V, which is minus 1.2. this is coming out to be around minus 14 volts. I'm missing a decimal somewhere, just give me a second. So I4 would be V minus V naught over R4, that's 91, this will be around 10. So V minus V naught, this will be around 11.1, so V naught will be 12.1 V. Oh sorry, this is not 10.2, this is 1.02. This is not 10.2, this is 1.02 actually. Yeah, this is 1.02, this is 1.02, 1.02, 1.02, this will come out to be 0.12, and then if you multiply it over here, which is V is minus 12.1 times 0.12, so 12.1 times 0.12, 12.1 times 0.12 comes out to be minus 1.45, which is the closest option that we have is B. Again, to quickly summarize, what we did was that the problem was given, and due to the virtual short condition we assume this node to be V, and then we simply apply KCL at inverting as well as non-inverting terminal. So this is an unknown V and the other unknown is V naught, so hence we require two expressions, which we obtained, and then we just put the value from one of the expressions into the other to arrive at the expression the value of V as minus 1.45 volts. So this is a different problem in the sense that this is not directly a negative and positive feedback, but you can again see, since we had applied the input, this is the input signal of 0.4 volts to the inverting terminal, the output voltage is negative, input voltage is positive, output voltage is negative. This means again we are operating in the same regime, that since voltage is applied to the inverting terminal, the output should be out of phase with respect to input, and hence that's what this negative sign denotes. This is actually V naught, not V. V naught is minus 1.45 volts, and since we are operating in linear region, you can see that this gain is not very high, 0.4 to 1.45, right? Open loop gain, if you recall, is 10 to the power 5 or even higher. Here the gain is very low, right? If you divide 1.45 by 0.4, this is not even 4 times, maybe 3.5 times, minus 3.5. That happens because of the feedback. So again, even though we have read the formula, when you solve this problem, just try to recall those formula, that it should be minus R2 over R1. Is it that? It's not that. Why is it not there? So these are the typical ways in which you tend to understand those problems. Okay, now let's move forward. Again, a very similar problem as we saw before. We again require to find V naught over Vi. So the circuit naturally has changed, but our approach as always will remain the same. We'll first do some pre-checks. Since nothing is said about the ideality of op-amp, we'll assume, and the key things is that R out is 0, R in is infinity, and I in is 0. This means no current here and no current here. Okay, nature of feedback, what is the feedback that we see? Output terminal is talking to the negative terminal, so this is a negative feedback, and we have seen that in the negative feedback usually what we see is stable circuits, right? Virtual short, we can use that. We'll assume that it's operating in the linear region, and we'll eventually see what is the output voltage and is it saturating or not. All right, so the virtual short means these two potentials are approximately the same. So let's do the virtual short condition. This means this potential is also at 0 volts. Okay, let's label the currents. This is I1, this is I2, let's call this I4, and let's call this current I3, and let's call this node A. Okay, so first thing, KCL at non-inverting terminal. So incoming current is nothing but I1. Outgoing current, I'll assume no current here. It will be 0 plus I2, right? So I2 we get equal to I1, right? And which happens to be I1 we can clearly write as Vi minus 0. This potential is 0 over R1. Okay, so we'll see that in what ways can we utilize this information. All right, now second thing we do is KCL at node A. At this node, let's apply KCL. So we write incoming current, which is I2. This should be equal to outgoing current, which is I3 plus I4. So if I write I2 can be written as 0 minus, let's call this voltage V, some voltage V or VA over R2. This will be equal to I3. I3 is nothing but what's I3? I3 will be VA minus V0 over R3. I4 will be nothing but VA minus 0. This is 0 over R4. Alright. So what we don't know here is VA. How do we find VA? We know I2 equal to I1. So if I solve this I can write as Vi minus 0 by R1 is equal to 0 minus VA over R2. This is I2, this is I1, right? So from this I can get VA equal to minus R2 over R1 times Vi. This is the expression that we obtained. So this is for the first part. So VA will be negative sign, and the factor will be R2 over R1. So now let's just find out V0 in terms of VA, and then we'll be fine. So let's put the values. Maybe something will get cancelled. The value of R2 is 9.1K. This is VA minus V0 over R3 is 8.2K plus VA over R4. R4 is 4.7K. If I solve this will be VA minus V0 over 8.2K. This will be minus VA will come out common. I can get 1.9.1K plus 1.4.7K. As effectively they are in parallel. Okay, so let's now solve this here. VA minus V0 over 8.2K. This is equal to minus VA, and the two parallels are 9.1 and 4.7. So let's see what's their parallel combination comes out to be. 9.1 times 4.7 divided by their sum, which will be 13.8. okay, this is coming out to be 3.1. so this comes out to be over 3.1K. okay, so from this I can get VA minus V0 equal to 8.2 by 3.1, 2.65 minus 2.65 VA. This gives me V0 equal to 3.65 VA. So V0 is equal to 3.65 VA. This is the second expression. Now what is VA? We already know that VA, you see VA is here. So VA is nothing but minus R2 by R1 times VI. 3.65 minus R2 by R1, this is multiply, times VI. From this I get V0 over VI equal to 3.65. Negative sign, R2 is 9.1K, R1 is 1.2K. So I'll simply put those values. That will be 9.1 over 1.2, sorry, 1.2. This comes out to be 27.65 minus 27.65. Closest option is C. And as always, we'll just verify some of the things, that since the input is being applied to the negative terminal, this means it's an inverting amplifier. So output voltage should be out of phase with input voltage. Hence the negative sign, which comes out to be this, right? And again, since okay, there we are not talking about what is the VI, right? But since we have assumed we are talking about gain here, so gain makes sense only when you are operating in linear region, because in saturation region, whatever input voltage you apply, output voltage will be plus Vsat or minus Vsat. So we talk about gain only in linear region, then only it makes sense. So remember the assumption of the virtual short, that makes sense because we are operating in the linear region and there's a negative feedback as you see. So again, a straightforward problem that we had, just using the KCL at this node first, and eventually this is the important thing, KCL at this node, and just simply writing the expression, and rest is just algebra. So there's nothing much to be worried about over here. All right. Okay. Jumping to the next problem. For the op-amp circuit shown in the figure, what is I1? So there is a current I1 that's flowing to the 4K resistor, where we are required to find that value, and let's assume this voltage to be V0. Again, the pre-checks, we'll assume it to be ideal if nothing is said about it. This means R out is 0, R in is infinity, and I in is 0. This means no current flowing here, no current flowing here. Nature of feedback. So feedback, we say output is connected to the input side. So again, you can see it's connected to both sides, but there is a negative component. And plus the input is also applied over here, right? So whatever output is being fed, right, here they're fed through different resistors, so that also plays a role, and we'll see how it says virtual short. Again, we'll assume it operating in the linear region, and hence we'll assume that negative and positive terminal are sitting at almost the same potential. All right, so let's do that. So this is the node voltage V0, this we have grounded, right? Let's call this voltage some voltage, let's call this V1. So that if this is V1, this will also be V1 because it's just a wire. Okay, so in the first step, what we'll do, we'll label some currents first. Okay, let's call this current I2, let's call this current I3, I4 and I5. Again, no current can flow here or here. Okay, so if we see KCL at inverting terminal, the incoming current is I4, outgoing current is 0 plus I5, right? So let's, I4 expression would be Vi minus V1 over 1.8K. This should be equal to I5 is nothing but V1 minus V0 over 1.8K. So they get cancelled. This will give us a very nice, so this will be Vi minus V1 equal to V1 minus V0. So we are required to find I1. Okay, Vi we already know, right? So what I can do that is I can find V0 from here. So V0 would be 2V1 minus Vi. This means V0 would be 2V1 minus plus 1 because the value of Vi is minus 1. So that is our expression 1. Now what I'll do is now KCL at node A. Let's call this node A. Okay, so I3 will be flowing here, remember that. Why? Because no current can flow here, right? So incoming current would be I3 plus I2. This is also incoming. Outgoing current will be nothing but I1. What's the expression for I3? I3 can be, this is the same current here. I can write 0 minus V1 over 2.2K. I2 will be nothing but V0 minus V1 over 2.2K. V0 minus V1. I1 will be nothing but V1 over 4K. Okay, so let's do that now. So 2.2K will go to the right side, so I can simply write it as minus V1 plus V0 minus V1 equal to 2.2 V1 by 4, right? So that comes out to be 0.55. This right side comes out to 0.55. So I'll get V0 from here equal to, this will be 2V1 plus 0.55 V1. This will be 2V1, right? And this term will be 0.55 V1. This is the expression 2. Now we'll equate simply 1 and 2. So 1 is equal to 2. We'll get 2V1 plus 1 equal to 2V1 plus 0.55 V1. This gives us 0.55 V1 equal to 1, and V1 will be equal to 1 divided by 0.55, which comes out to be 1.82 volts, and current I1 is nothing simply but this node. This was the potential V1, right? V1 minus 0 over 4, so 1.82 over 4, this comes out to be 0.45 milliamps. Okay, so option question number 7, option is D. Yeah, that's the correct one. Now quickly to summarize what we did, was that we first using the inverting side, on the inverting side we found out a relation between V0 and V. This is the potential V1 that we had assumed, right? And then finally by applying KCL at this node, we again got an expression between V1 and V0, because these are the two voltages involved here. Again two expression, two variable, we eliminated V0 and we got the expression for V1. Once we know V1, and then we can simply find out the current I1. Now again, a key thing to note here is V1 is positive 1.82 volts. This means V0 will also turn out to be positive and V in is negative. So again you see V in is negative, V out is positive, phase shift of 180 degrees again, which is happening because input is being applied to the inverting terminal. So again we keep on I keep on emphasizing the same thing. It's important that you correct your self value solving the problem itself. Okay. Now this is a good question. V0 equal to K1 V1 plus K2 V2. This is what we typically see in superposition, right? So that's what we'll do. What is K1, right? So again the pre-checks, we'll assume it to be ideal since nothing is said, and this would effectively mean that R in equal to infinity and I in is equal to 0. No currents here. And nature of feedback, you can clearly see it's a negative feedback because the output terminal is talking to the inverting terminal. In virtual short, we again assume it to be in the linear region, and so hence these two terminals we assume it to be at the same potential, right? So one way of doing it is that we solve this, make this node as V2 and we solve this problem, right? We're not going to do that. So what we know is that V0 equal to K1 V1 plus K2 V2, and we are required to find K1. So what I'll do is that in the first stage we put V2 equal to 0. So what effectively means is that this is grounded. This is grounded. By virtual short, this potential will also become 0. Okay. Now I'll apply KCL at inverting terminal. KCL at inverting terminal. So let's do that. Let's assume this current to be I1, this current to be I2, this current to be I3, this current to be I, which will be 0 because remember ideal op amp. So I'll write incoming current is I1 plus okay, so you see that this, so whatever current is flowing is here. Okay, so I should have said that this current will also be I1, not at KCL, not at inverting terminal. So I should have said KCL at node A. So incoming current would be I1 plus I2. I1, this current would be I1 because there's no current flowing in this op amp. So I1, this all current will flow here. So I1 plus I2 should be equal to I3. Okay, the value of I1 would be V1 minus 0. V1 minus 0 over 5K. The expression for I2 would be 0 minus 0. Note this potential is at 0. So VA is also 0. 0 minus 0 over 15K. This is I3, which is nothing but 0 minus V0. This is again 0. Remember, VA is 0 over 10K. This term gets cancelled, so I get V1 over 5K equal to minus V0 over 10K. So what I get is V0 equal to minus 2V1. Simple, you cross multiply it. So it's supposed to be of this form, right? If you put V2 equal to 0, if I compare it, K1 V1 plus K2 times 0, by comparison I can see K1 equal to minus 2. This is I'm seeing by comparison. By comparison, K1 is minus 2, which happens to be option C. So I'll summarize it after we do the next problem in this set, okay, so that they go together. Now we are required to find the value of K2, right? So to find K2, I'll write again V0 equal to K1 V1 plus K2 V2. K2 is what? So in this case we put V1 to be 0, right? This means you ground this. And again we apply the same rules that we had. So this is the virtual ground. So this will be V2, potential V2, and this will also be V2. Again, no current can flow in either here. So again I'll write the KCL. So this is I1, same current I1 will flow here. Sorry, this is I1, this is I2, and this is I3. This is the potential, this is the node A, this is node A. So secondly we put KCL at node A. So let's do that. So that would be I1 plus I2 equal to I3, that's incoming equal to outgoing current. This will be 0 minus V2 over 5k plus 0 minus V2 over 15k, that's I2. This will be V2 minus V0 over 10k. Okay, if I sort it out, this will be minus V2, this would be 3 over 15 into 4 over 15k. This would be V2 minus V0 over 10k. If I solve this, it will be V2 minus V0 equal to, that will be 40 over 15. So 40 over 15 comes out to be 2.67 minus 2.67 V2. So here V0 will simply come out to be 3.67 V2. Again you compare it with K1 V1 plus K2 V2. Remember V1 equal to 0, this term vanishes. So if you compare it, so we can say that by comparison K2 is 3.67. Let's see if there is an option. Yeah, there is an option, D. Okay, so what we did here was that since it was given that superposition form, so we deactivated V2 and we solved just as if V1 is given. So in this case it should be an inverting amplifier, right? And we saw that we got the answer as -2, which means it's an inverting amplifier. When in the next time when to find K2, we deactivated V1 like this, right? And this is a non-inverting amplifier, so we should see no phase change, which we see here. And then you can write the complete expression, so that's not a big deal. Okay, now building upon this now quickly. So now we have for the circuit shown in the figure, what is V0. As always, we'll assume, if nothing is given, assume it to be ideal, and we have been seeing that, but this essentially boils down to I1 in equal to 0. So there's no current here and there's no current here. Nature of feedback, you see it's a negative feedback. It's a negative feedback because output voltage is connected to the inverting terminal. Virtual short, we again assume it to be operating in the linear region, and it's a stable output, negative due to the negative feedback. And so we'll assume the virtual short, which would mean that these two terminals are almost at the same potential, right? We are required to find V0, so we are required to find this due to the virtual short. So this node is at 2 volts, 2 volts, 2 volts, right? We are required to find V0. That's fairly simple. We call this current I1, we call this current I2, we call this current I3. It's very similar to the previous problem, right? So the same current I1 will be flowing here, and let's call this node A, right? So we'll apply KCL at node A. When you do that, so we can write incoming current. There's no current flowing here, so I1, which is coming here, will flow in this branch upwards, will not go into the op-amp. So I can write I1, the other incoming current is I2. This should be equal to outflowing current I3. I1 I can write it as 2. Note this potential is 2 minus whatever this potential is, which also happens to be 2 volts, over 1.5k plus I2. I2 is this, so that's 1 minus 2 over 1.5k again. This should be equal to I3. I3 will be nothing but 2 minus V0 over 820 ohms. Okay, so this term vanishes. We'll get 2 minus V0 over 820 equal to minus 1 over 1.5k. Just a second. Yeah, so 2 minus V0 over 1.2k, and from here what I'll get is, let me solve this. So 820 over 1500 comes out to be 0.55. so this is 2 minus V0 equal to minus 0.55. From this I'll get V0 equal to 1 second, this will be 2.55 ohms. I'll write it again. So V naught coming out to be 2.55 volts. Okay, so let's see if there is an option like that. 10th A. Yeah, again a straightforward problem. This is actually the fourth problem in the same row, like we have provided two inputs over here. So effectively what happens is that this is not playing any role, because this potential is the same. So effectively only the current is flowing through the top branch. So whatever current is being provided through this, it flows through here, right? Again you can see that since this is not playing a role, so this is so your reference voltage is kind of I should not say reference voltage, but your a non-inverting terminal is sitting at a higher potential as compared to the inverting terminal, which is over here. The 1 volt is driving the current. That's why you see a positive voltage over here, right? Right. So moving forward, now these are three very interesting problems than the next problems that we are going to talk about, right? So in this, the question says, in the circuit shown in the figure, op-amp operates in open loop configuration. So the problem itself says there is no feedback. You can clearly see there is no feedback. What is the duty cycle D, defined as fraction of time V naught is high? We already talked about what is T. That's when it's high. If the wiper is in the top position, so this is a variable resistor, right? And the wiper is in the top position, but this would mean is that this is touching here. We'll talk about in this. So we'll talk about in the top position, okay? And this is the input waveform that is being given to us. So essentially, we need to find out when the V naught is positive. So when the V naught be positive, we know that. So let me draw the. So again, ideality of op-amp, we'll assume it to be ideal. This effectively what we're interested in is I in is 0, so no current flows here, okay? And nature of feedback, there's no feedback, it's open loop, right? So the problem of virtual short is I mean, since we are saturating from one region to another, right? So here it's of no relevance, right? We cannot talk about this here because this virtual short applies in linear region, and we are talking about saturation region. So we'll swing maybe from here to here, something like this. This is something V out will look like, okay? So let's do. Now we are talking in the top position. So what does mean in the top position? So this resistor, this will come here, right? So effectively this potential is the same as this potential. This means this 2.2k is equal to 0k. It's shorted. Wiper is in the top position. This means this potential is the same as this potential. There's no resistance. All right. So what I'll do, I'll simply try to find out what is this Vref. Note that this input voltage will compare it to the Vref, right? So as a step 1, in top position, find Vref. How do you find Vref? So there's no current flowing here, so all the current will be flowing like this, correct? So Vref will simply be 0. Note, this potential is the same as this potential, right? So if Vref is 0, this means now we can draw the output waveform. So let's do that. So this is your input waveform. I'm only drawing one cycle because that is what we bother about, right? So this is your V in, and let's draw Vref in a different color. Vref is what? 0. So I'll draw this here. This is Vref equal to 0. So we know that what will the output voltage? The output voltage V naught equal to high when V in is greater than, or Vref. V in is the positive term, so V in is greater than Vref, it will be high. It will be low when V in is less than Vref. So in this part, V in is higher than Vref, so V out will be high. So it will be high. And here it will go low because V in will become less than Vref. It will go low. It will go like this. It will be a perfect square wave. Okay, then it will again go up. You can clearly see. So it's on only half the time. This is a triangular wave, so we can see that. So if I consider this time to be t, this time to be 2t, again this will be t and 2t. So duty cycle D, right? Duty cycle D will be V output when it's on over V output on plus V output off. So this will be t over t plus t over 2t, which is nothing but 0.5. 0.5 will evaluate to, as we see, the 50%, just expressing in terms of decimal, sorry, in terms of percentage, that's all. Okay, so the key thing to note in the top position, so essentially whatever the potential here, this will behave something like this. So this will be bypassed completely, like we saw in the bypass capacitor, right? This is something like this. Okay, now it says it's in the middle position. What's a duty cycle then? Again, it's in the middle position. This means that 2.2k will not be 2.2k, it will be 1.1k. Okay, so let me write this. In middle position, R variable, this is what I call the R variable, this is nothing but 1.1k, right? And again we'll assume this to be Vref. So again this is a potential divider, right? So Vref will be equal to 10 times R variable over 3.3 plus R variable. I'm just applying in this circuit. Okay, so current will flow something like this, because no current can flow here, remember that. So this will come out to be 10 times R variable is nothing but 1.1 over 3.3 plus 1.1, so that will come out to be 2.5 volts. So Vref now we have obtained has come out to be 2.5 volts only. Okay, remember it was 0 last time. What I'll do is I'll do the same thing again. Let's draw the input waveform, something like this. V in, and now we'll label the V out. Just before that, let me choose a different color. Vref we obtained is 2.5 volts, so this is, let's say, 2.5. So V output will be high after this point and up to this point. So V output will be high. Why? Because we know V output is plus V sat. If V plus in this case is V in, this is nothing but V in. If V in is greater than V negative is nothing but Vref, that is the voltage here, Vref, and minus V sat if V in is less than Vref. So here it will be 0, right? And it will go like this. So what I'll do is I'll only consider the one quadrant. Okay, and let's try to find out what is this time. Let's so we know that this was t, this was 2t, this will be t by 2, half of it, and this will be, let's say, some time t naught, and this is a linear curve, right? So I can simply say that if I compare these the slopes of them, right? So I can simply say Vref, so that will be Vref over T naught should be equal to Vmax over T by 2. Vmax is reaching here and Vref is the voltage here. This is Vmax. Okay, so if I calculate this, I'll get T naught, this should be equal to T by 2 times Vref over Vmax. What is Vref? Vref is 2.5, Vmax is nothing but 12. So if you solve this, this comes out to be 2.5 by 24.1. T naught is coming out to be 0.1 t. So this time is 0.1 t. And again, what will be this time? This time will be 0.1 t less. So this will be 0.9 t. And remember, the complete cycle is 2t. This time is 2t. So what is the duty cycle? Duty cycle is the on time. On time is only this. This will be 0.9 t minus 0.1 t divided by 2t. This is 0.8 t over 2t. This comes out to be 40%. Very simple round figure, very nice round figure, to 40%. How did we solve this problem? Again, since the wiper was in the middle position, so this will become 1.1k, and we found out the Vref. The Vref came out to be 2.5 volts. Okay, and so when this red curve crosses Vref, then only it will be on. How do you find this time t naught? By using this, because the slope of, or you can say similar triangles, whatever you want to call it, this is the thing that you want to do. And we do this, we obtain 0.1 t, 0.9 t, and finally we obtain the final answer to be as the 40%. Okay. Now next problem in this set is when the wiper is in the bottom position. Wiper is in the bottom position. This means it's somewhere over here, right? This means we will see complete 2.2k, but yeah, we'll see complete 2.2k. So again I can say r var will be equal to 2.2k. Okay, and now we'll again, as always, we'll try to solve this problem. Again, remember, ideal op amp, so there'll be zero current flowing over here and here. This is what our Vin is, right? So what I'll do, and this is the Vref. Okay, so Vref I can find using the potential divider. So Vref will be equal to 10 times 2.2k divided by 2.2k plus 3.3k. Again, remember, this is no current is flowing here, so all the current has to be flowing here, and that's why this is a potential divider. This will come out to be 10 times 2.2 by 5.5. This comes out to be I think 4 volts. Yeah, 2 by 5, 4 volts, correct. So Vref we have found out to be 4 volts. Now what we'll do is simply draw the waveforms that we have been drawing. So this is your Vin, only one cycle, Vin, and we'll draw the output waveform in purple. So this is your output waveform. Okay, this will be your output waveform. This is your Vmax, that's plus 12, and your Vref is what, 4 volts. So Vref is somewhere over here. This is Vref. Okay, again we assume this is the time t that we know. This is 2t, and this Vmax we know will be achieved at t by 2, and we'll assume this crossover time as t naught. Okay, and we know, since now consider the time between 0 and t naught, right? Now I'll write V out equal to high. When is it high? When V plus, which is in this Vin, is greater than V minus. V minus is nothing but Vref. Vref is, remember, 4 volts, and it is low when Vin is less than Vref. Okay, so this is the V reference. So in this portion from 0 to t naught, Vin is less than Vref, so it will be 0. V out will be 0. This is V out. V out will be 0 in this time. V out is 0. Then during this time between t naught and t by 2, Vin is greater than Vref, so we'll have V output high. So V output will jump here to high. It will remain high until this point, right? Until this point it will remain high, and then it will go low, and then it will remain low until time 2t. So this is time t naught, and also accordingly, so this time will be t minus t naught, because the slopes are the same, right? Rising and falling. So this will be t minus t naught. Okay, how do we find t naught? Now again, t naught you can find out using the property of similar triangle or whatever you want to call it, using the slope. So we find t naught. This is step 3. So we can say that it will be the y-intercept, which is Vref over t naught. This should be equal to Vmax over t by 2. From this we get t naught equal to Vref over Vmax times t by 2. Vref is 4, Vmax is 12. This is t by 2, so this comes out to be t by 6. T naught comes out to be t by 6. Okay, now duty cycle D, if you recall, will be this t minus t naught minus t naught, t minus t naught minus t naught over 2t. This is the complete into 100. Okay, so this will be t minus 2t naught over 2t into 100. So this comes out to be t minus 2t naught will come out to be t by 3 by 2t times 100. This will be 2t by 3 over 2t into 100. This comes out to be 33%. So option A, 13, option would be A. So now we have completed these 3 set of problems regarding the where we have the variable resistor. Depending where the wiper is, that is the variable resistor value will change. Accordingly, Vref changes. So remember, this is the Vref. Accordingly, Vref changes, and then due to the change in Vref, so you get different duty cycles. So what this means is that effectively the application is that just by changing the position of wiper, you can get different duty cycles. So you can generate different waveforms. Let's say you want this output to be fed to some circuit that you want, right? So what you can do from this is that just by changing the value of this the variable resistor, you can generate different duty cycles. So that's a good application to have, I believe. Okay, now coming on to the second last problem for today. The circuit shown figure, what is V naught? Quickly, again nothing is said, so let's assume ideal op amp. What this effectively means is that R in infinity, R out is 0 and I in is 0, right? So there's no current flowing here. Okay, and second thing is that what is the nature of feedback? So as you can see in this problem, output voltage connected to the negative terminal, so we can say it's a negative feedback, which means stable circuits. And again for virtual short, we'll assume it to be operating in the we'll assume operating it to be in the linear region. Okay, and thus we can assume that AV is high enough that V plus is approximately equal to V minus, which means virtual short. This will behave something like this, almost the same potential. All right, we are required to find V naught due to the virtual short. This will be like this. This means the potential here would be 0, right? What we do, we'll simply apply KCL at inverting terminal. So when we do that, again assume this current is I1, this current is I2, there'll be no current flowing here, so I can write incoming current I1 should be equal to outgoing current, which is I2 plus 0, because no current flows through goes into the op amp. The value of I1 I can write as 2 minus 0 over 4.7k. The value of I2 I can write as 0 minus V naught over 1.2k. This will give me V naught equal to minus 2.4 over 4.7. This comes out to be 2.4, slightly less than 0.5. Sorry, slightly more than 0.5, 0.51 volts, minus 0.51, sorry. Negative sign again denotes that these are out of phase, which makes sense because the input is being fed to the inverting terminal. So output will be the opposite sign as the input signal. So we obtained V output is minus 0.51 volts, which happens to be option C. This is I think this is the simplest problem that we had solved today. All right, so we have obtained the value of V naught. So let's now jump to the associated problem with this. In this is the same problem as we had just solved. In this, now we are required to find what is the value of I1. So I1 is the current flown that is through here, and we already know that V1 we obtained is minus 0.51 volts, right? And so how do we do this? So remember, this current we assumed it to be I2. Okay, I should not have taken that current to be I1. Sorry, just a second. Let's take this current to be I4. Okay, there will be confusion. Okay, so now what we want is this was I1, this is I1, and let's say this current to be I3, right? So what I'll do is that we'll simply apply KCL at output node, the node V naught. So let's do that. The incoming current would be I2, other incoming current is I1, the outgoing current is I3, right? So we are required to find the value of I1. So I1 would be simply I3 minus I2. Expression for I3 would be V naught minus 0 over 2k, minus the expression for I2. I2 would be, this was 0, remember, virtual short. I2 would be 0 minus V naught over 1.2k. So this will be V naught over 2k plus V naught over 1.2k. This will be V naught times 3.2 over 2.4k. Now let's put the value of V naught, which we obtained minus 0.51 volts, so that will be times 3.2 divided by 2.4. It comes out to be minus 0.68 milliamps. The milliamp comes due to the kilo ohm terms that's in the denominator, so which happens to be minus 0.68 milliamps. Let me check. Yeah, this is the correct option that we have. So minus 0.68 milliamps, right? Okay, so that completes a set of that completes the session for today. But just before we close, just a couple of remarks. So you see this I1 is the negative sign. The negative sign, you must be aware, is the sorry, yeah. So I1 is of I1 is negative sign. What this means is that the direction is reversed, right? Instead of current flowing from left to right, the current is actually flowing from right to left, right? So this means that what this means is that since this, what we can conclude from that op amp is sinking current, right? This op amp is sinking the current because this current is negative. This means current is flowing in this direction. What would effectively mean is that, so whatever current is being provided, like through this branch, so only a small fraction will be going to the output. So that happens because the way you want to drive the load, and you remember it also depends on all these resistances. The key takeaway is that that you can tweak the current flowing through the operational amplifier just by tweaking this voltage. And by tweaking, how do you tweak this voltage? Now if you remember that the famous expression for voltage gain for inverting amplifier is I believe is RF over R1, where this is RF and this is R1. Yeah, so this is, so based on, excuse me, sorry, so based on the values of this, you can obtain V0, and thus the amount of current that you can drive. This is typically your load RL that we denoted. You can determine the current flowing through here. And secondly, by playing with this value of resistor, right, you can also determine what amount of current will sink into the op amp, because all these op amps will have some current ratings also. If you cannot sink an infinite amount of a large amount of current, right? It can be 5 volts, 20 sorry 5 milliamps, 20 milliamps, 25, 50 milliamps, whatever it is. There will be some voltage current rating for this operational amplifier, right? So these are some practical things that you may come across, and it's beneficial to just keep them in your mind. I just say this is for inverting, and as always, negative denotes the phase shift of 180 degrees. Okay, so that's it from my side. I have we are just in time, and we have completed the problem set for today. I'll stick around. If you have any comments or uh, doubts, feel free to ask, and if not, we'll close the session. Gautam,
Yes, sir.
any doubts that you have?
No, sir.
Okay, then I guess thank you for your patience. Thank you for your time. I hope to see you next week. Mm, I'll be now closing the session. Okay.
Okay, sir.
Okay. Thank you. Have a good night.